morning, friends. We have been talking about thrust required, power required. We have talked about for thrust required CL by CD should be maximum. For power required CL3 by 2 by CD should be maximum. Now by now aware what will be the speed. Okay. I'll be going little one step ahead in understanding what is the meaning of thrust required minimum via CL by CD maximum. Okay. So this is thrust required versus CL by CD, a closer look. Okay, let us see. We are very comfortable writing this W by CL by CD, and this means thrust required minimum implies I must fly at CL by CD maximum. Let us do a little bit of algebra or some sort of a little mathematical insight into this CL by CD max. Okay. See, we know CD is CD naught plus KCL square, and we know that this is parasite drag and KCL square is the induced drag. All these things are very clear to us. Now if I ask a question, what is that CL I should fly so that CL by CD is maximum? If I want to find out mathematically, I can follow this few steps and get an answer. This I will write CL by CD as CL by CD naught plus KCL square, and I will differentiate dCl by CD by CL, and if I do that, I find CD naught plus KCL square into 1 minus CL into 2 KCL divided by CD naught plus KCL square whole square. Now next step is I find the turning point. So I put this equal to 0. If I put dCl by CD by CL equal to 0, then I get an expression CD naught plus KCL square minus 2 KCL square equal to 0, or I get the popular expression CL equal to under root CD naught by K. As simple as that. Okay. You can check the second derivative to see if it is indeed a condition of maxima. Right? The second derivative should be less than 0. Okay. Now the interpretation demands CL equal to CD naught by K. When I write like this, once I solve this, what did I get? I get CD naught equal to K CL square. How do I give an interpretation? Let us draw thrust required versus speed, and we by now know that this is the induced drag or induced thrust component, and another was parasite, and this was the net thrust required. Okay, and this was the point where thrust required was minimum. Correct? And thrust required was minimum. As far as we understand, this is the point corresponds to CL by CD maximum. But from this analysis or this one, what did I get? That is the point where the parasite drag equal to induced drag. This is in terms of coefficient, so I call CD naught equal to KCL square. And you could see that this is indeed the point of intersection of parasite and induced drag. So this point and this point are same point. So we are now trying to add a little bit of mathematical value to our understanding. Okay. Second thing. So if I am flying at CL equal to CD naught by K, that means what is the CD I am flying actually? I know CD equal to CD naught plus KCL square. Since at this point CL is nothing but CD naught by K, or KCL square is nothing but CD naught, so my overall CD becomes twice CD naught. This is very important. So you can understand, if you are flying at thrust required minimum, that means the airplane designer should ensure that CD naught should be as low as possible. Okay? That means it calls for aerodynamics to work more and make sure the drag component at alpha equal to 0, which is CD naught, or CD at CL equal to 0, CD naught should be as low as possible. It should have a lesser skin friction drag, lesser pressure drag, and that is what is important for our interpretations, right? That one should be very, very careful and translate this to designer's mind. Okay. Now, the second part you see for flying with thrust required minimum, we have this. Flying with power required minimum, we have already seen that it is 3 CD naught by K. Let us take an example. Let's take an airplane whose aspect ratio is, let's say, 20, large aspect ratio, like a glider. And large aspect ratio, why? We are tempted to have large aspect ratio because if we are thinking one dimensional, that induced drag should be low, induced drag should be low, then one of the option is make the aspect ratio as high as possible, right? So let's say aspect ratio is 20 and let's take E is 1, let's say elliptic distribution, and CD naught realistic value I will take as 0.020, okay, which is a little lower side, but a good airplane will have this range of CD naught. If this is the data I have, what does this mean as far as CL is concerned? CL is CD naught by K, that is for thrust required minimum, so that will be 0.02 divided by K. What is the value of K? K is 1 by pi aspect ratio E, and that is 1 by pi into 20, and into 1 I have taken the value of E, assuming perfect elliptic distribution. So K is basically roughly equal to 1 by 60, right? The approximate, with pi I have taken just 3, not 3.1416. So if I put that value of K in this expression, what the CL I get is 0.02 into 60. And that is, if I calculate, it will be around 1.1, because this is around 1.2. Okay, under root of 1.2 is 1.1. So what is the message? The message is, if I want to fly at thrust required minimum, the CL should be 1.1. Now, the moment CL is 1.1, I get an alarm. I immediately see what is the CL versus alpha for my aircraft. And we know that this maximum value is for normal case, without any high lift devices, etc., etc. This value is typically for most of the business aircraft of 6-seaters, 7-seaters, 8-seaters. They are around 1.2. Even without any high lift devices, most of the airplane will have CL maximum value of around 1.2. Now you are demanding the pilot to fly at CL 1.1. See the problem? Slide, already he is operating somewhere here. So he is near this region. So just putting up a condition that CL you need 1.1 is not sufficient. Okay? So your design should ensure that whatever CL you are demanding to get thrust required minimum, it should be consistent with this back of mind. Are you able to get this understanding? Because you will see the seriousness. If I want to fly at CL power required minimum, then the CL value will be furthermore root 3 times 1.1. Where from will get the CL from normal aircraft? So the question comes, should we go for aspect ratio 20? All the induced drag was reducing, but there are so many other issues. So as a designer, you have to be multidimensional. You cannot go on giving maximum weightage to only one parameter, right? That is why I wanted to share this experience with you. Okay? We should also be careful to know what are the other silent features which is to be known before I talk about fly at CD0 by K, etc., etc. This is for thrust required minimum. This is fine that you need to fly at CL equal to CD0 by K to ensure thrust required minimum. Nobody is contesting that. But what is our main purpose? Main purpose is I want to fly at a particular altitude. Let's say that altitude is rho. I am talking about density. My purpose is I have to ensure that lift equal to weight. That is, I have to ensure that half rho v square SCL is equal to weight. And that means I need to fly at 2 W by S by rho CL, and the CL is nothing but dictated by this for thrust required minimum. So this is 2 W by S rho CD0 by K. Now see, interesting part. If we are flying at a particular altitude, the velocity should be this much to ensure that thrust required is minimum. When you are flying means you are cruising at altitude where density is rho. But this will give some value of V. Okay? Now, where from I'll get the V? The moment there is a V, I know that I need to have an engine which should be able to give me enough power or thrust to generate that V. That is, thrust equal to half rho V square S CD. Okay. I need to have enough thrust so that I get this much of V, because as the V is increased or for a particular V, this airplane will experience a drag. So I have to ensure that my engine is enough powerful to give that much of thrust. So there again I go back to the engine side, whether really this velocity is achievable or not. If it is achievable, fine. If it is not, then I will be, if I want to reduce this V, I will try to play around with the wing loading W by S. I will try to reduce the wing loading. Okay? And that is how this iteration will go on happening. Right? And finally you get a configuration where you are giving enough bandwidth to your pilot so that he can get those solutions by looking at the instrument, getting those numbers and maneuvering the airplane to that conditions. Because if your design doesn't have those conditions which can be expected by a pilot, then he will not be able to fly at that conditions. So it's the primary role of a designer to make sure you have given all those solutions in the design itself, and the pilot starts gaining into those domains and try to fly the way it should be flown. Okay?